But yeah, it's a nice place. It's equipment, but the actual company was so they got they basically have a pyramid after yeah, right? Well, I learned it because warehouses built on pyramid. But yes, the Finance organization in pyramids are one of the framework, but it used to be so you moved on, and then they refounded it. But it's one of those. It's not that. I mean, it's got its own close but it's nice. Feels like that, but doesn't matter. What it is, they just really well. Yeah. And I think that's what we have. That's how we oh, they was it supposed to well, they know, but they still kind of pretend but in a business sense, it does teach others and it does, and they don't be acquired. So
it doesn't seem like we're ready to start.
But now there's
streaming starts automatically.
It's already on.
It's already on.
I'm getting to just leave. No, not at this very moment. So I have a colleague who's on now. Would you like to reveal yourself?
Yeah, it's basically analog, very badly designed schema.
The phone ranges everywhere.
Just I did this art generator thing.
Crystal.
Can you hear me?
So Crystal will start the stream as soon as you're ready. So as you're about to go live, which will be about what time do you reckon? What time do you reckon?
Well, I think the question is last for like 20 to 30 minutes. They want to be wrapping up at 8:30. So it's going to be
7:30 later.
So I can make it up to you. If you're here, I mean, Crystal, you can hear us, right?
Crystal, you there?
Yeah, I can hear you guys.
Also, assume you're on Slack. Are you on Slack, Crystal?
It's like
Crystal.
This is like stupid stuff. Yes, teaches message me on always try all these things are frustrating that you kind of get used to at the end.
I'm an IRC person, sorry.
We had that conversation the other day in our channel about Crystal, I'm going to pass the host your Slack information and he will ping you when he's about to start because I'm going to shoot off soon. But everything seems to be fine.
Yes, you guys need to go. She doesn't know why we did earlier, but we can't hear you now.
Yeah, we could earlier. I think it's the her headset or something.
Not only that, it's not yeah, but use that because it says kind of depends on each other, so you have to be careful. I know. People say, yeah, the first layer, normal, especially at the edges, the second layer, the corners, the next layer,
Yeah. She's saying she wants to know screen share deck end view, which is fine.
So we're doing this section, and then naturally on the person, but they can actually see because we've zoomed in to whoever's there. So you can actually zoom in more, but because I don't know if there's discrepancy between height and etc. So I've given it as best as I can.
Yeah. So she's saying for the Emma stream she can't do side by side of the screen share and speak. So that's no problem.
If you do need to use this, volume, if you wanted to see like the self view, for example, on the stream, if you ever wanted to look on it on your laptop, or someone says, "Oh, I can't," pings you and says, "Oh, I can't. Can we zoom a little bit further into the version?"
Yeah.
Then this just controls the camera. Okay. And you just, where it is now, you can literally go where it is, and you just press zoom.
We had a configuration.
Okay. Sounds good.
That should be it.
Well, if you want to shoot off.
Yes, but
we have already overstilled.
It's also behind
speakers. If you open the room, you can see them one on either side of it. They are on.
I don't know how that's set up here. These are run.
If you want mics,
The same, like,
it's just a different one. Give me a mic, just different.
I like it, but
That's because we have this
slowly.
right to things correctly. So I don't know if there's a lot of interaction from the person. Because that's all.
Yeah. Yeah.
Oh, you're right. Do you think there's going to be more?
Well, I know it's like first.
Yeah, same.
No, 7 seems a bit much, but maybe we can.
That's a lot, yeah.
We can start right now?
Yeah,
We still need to
let's
try
announce.
No, that's fine.
We got 2 people waiting for the election.
So we do it.
Yeah. Oh, how's that?
Now,
That's what I'm saying.
Oh, well, why not just now?
You want to start now?
the second one to give the second one there. If your keys are there and you want to ask questions,
But this, presumably this is going to be picking up.
it will pick up, but I'm just giving you the added option.
Yeah, no problem. Understood. Okay. What's the verdict? Are we starting now or after?
Let's make it a order pass.
Give you more of an amplified voice as to how you
Getting that thing set up here, waiting for people. It's like another organization. Sure. That's why you had to when someone else doesn't say it, I'll step up. It might be me. I'm just
On the meetup list, so now I know who 8 is. Full name.
I wonder if like people are being lost or something, because I don't, like, it's not that hard to get you.
Are there any messages on the meetup that people
I
saying?
checked email.
It is a little bit of those. That's inside the building.
Yes, I
Once
think
you get the building.
Surely you're not wandering around the corners of where the hell am I?
You will succeed. Was it Mozilla that helped post it, or is the member? About 3 years ago, it was when Mozilla moved into this. Previously, we were at like Covent Garden.
Yes.
So they may have attended a meetup
Of
there.
Leicester Square?
Yeah,
Yeah.
and there was a much larger community space there, so you got a lot of
Very good bar there.
Yes, the splendid bar.
Nicer speaker. How come you moved?
then I think the landlord priced us out because we do some internal renovations. But also, we didn't have a lot of people who were frequently to make it work. Amount of space. This one is super small. She can keep the toilets.
Yeah, I work for a global. That looks nice. Where's he going?
Maybe yes. Okay, so a few minutes.
Yeah.
So should I do the let you know about the fire assembly points and things like that? So as you may already have been told, there's toilets just outside of the ladies, and on your left there's a stairwell go down one floor for the gents. The fire exit is that same stairwell. So as you get out of here, turn left, go all the way down, and take a left to exit the building. The fire assembly is another left and going back up to Southwark Street where there's a sushi restaurant called Itsu. Just outside that sushi restaurant is our fire assembly place. We're aiming to finish by 8:30 and get everyone out by 9. So I appreciate any help with getting us out on time. It's no smoking. There is a kitchen there, but there's no access to the snacks or drinks in there. But if you do need a glass of water or something, just let me know and I can get you that. There is Wi-Fi, it's Mozilla guests, and there's no password. So that's everything. Are you ready to go ahead and get started? Or
Yeah.
a couple more minutes?
It's good now, yeah. I mean, it doesn't make much of a difference.
Okay, so it will be streamed on YouTube and air.mozilla.org. This is the main view that will be visible. I think so this, just so you know, when you see the stream, it's not really going to be this. It's going to be mostly the slides. So it won't be quite as you see it there, as you can see. There you go. It's not on at the moment. The video will pick you up anyway, and possibly don't even need the microphone. But it's up to you. As long as you've got a loud enough voice.
Still need the microphone.
No. So these are microphones here, so they'll pick up.
Okay.
But that's just if there's questions, and we want to pass that around afterwards. So are we ready to start the stream?
Yeah.
Okay, Crystal, we're ready to start the stream. So if you want to go ahead.
Yes, you can go ahead.
All right, thank you.
All right, welcome to another Python meetup in London. First, we have Eisenbard telling us about a beautiful story of migrating from AWS Lambda to Beam, Apache Beam.
Okay, thank you. So yes, my name is Eisenbard Paulson. A little bit of background about me. I've had quite a varied career. I studied science. I've been a management consultant. Went back to university, became an artist. I've worked as an art lecturer. But for about the last 10 or 15 years, I've been working as a technologist. And so hopefully can share with you some of the things that we've learned recently over the last year or so. It's always nice to encourage other people to share in the things we've found out. So yes, so I'm a co-founder at a company called Huck, and we're a geolocation company. So we basically look at the macro behavior of people. So anytime we want to understand the way in which people are moving in the real world at an aggregated level, those are the kind of applications that we look at. So we partner with app publishers, and we help those guys, mostly small independent style guys. We help those guys monetize their users. We pull a bunch of data from those devices, and then we aggregate and anonymize that, and then we sell it into a variety of industries. So principally at the moment, that's finance, but also out-of-home media, property development. So anytime that you want to basically look at where are people going at kind of scale, essentially. I just draw a brief schematic of how it works. So we have an SDK which lives on the device, and that SDK is like gathering data, which is then submitted in batches up to our servers when the device connects over Wi-Fi. It's very important to us that we're very respectful of the power consumption, network consumption, and data consumption of the device, because we're essentially a kind of a guest in our host application. So we really, in order for us to be able to stay there, we need to not crash, we need to not use any power, we need to not use any network, etc. So those impose quite a lot of complexity in terms of the development of the SDK. Then when it's on the server, essentially we put it through a bunch of cleaning and aggregation processes. And finally, we then surface that to the client in a variety of forms, so they can receive it as JSON. And so clients who receive it in that way are mostly people who have quite a lot of in-house data science ability. So again, those are kind of people like your quantitative funds or other clients who are used to consuming tens of millions, hundreds of millions of rows of data per day. Alternatively, we provide a variety of visual tools for accessing it. So we have a bunch of dashboards that are built in Looker that back onto BigQuery, or you can buy direct BigQuery access. So clients who are buying in that form are more often small analysts, consultants, etc. So often those guys don't have the in-house infrastructure in order to consume the data. So just to talk a bit about the requirements of our technology, we didn't always sell the data in this way. Originally, the company was focused on providing analytics directly to app publishers. So providing those guys with ways of understanding the context of their users were in order that they could build experiences which are adaptive for those contexts. At that time, then, it was important that we be able to surface the data in close to real time. But as we've moved on and we have changed our focus in terms of who our clients are, that requirement isn't really with us anymore. So generally, we now provide the data 48 hours after real time. This gives us plenty of time to batch the data on the device, as mentioned, saving power, etc., and also time to perform the aggregation, clean up, and deliver that to clients in timely fashion that ensures that pipeline can stay up. Like one of the other main requirements is that we are often anticipating not what is going on at the moment, but what is coming down the line. So we've been growing continuously throughout our history. So we've been going about 4 years. We're currently processing about 250 million records a day, and that is still growing quite rapidly. So we often gather more data per device, but we're also ever seeking to have more and more larger panel, providing finer grained insight. So we need to be able to anticipate that future scale. So yes, we often like to have plenty of overhead. And finally, we need to be able to reprocess our historical data. So often we bring changes into the code base. Of course, we're continually making improvements in the way the data is analyzed, cleaned, and processed. But financial services clients in particular may have trained models against a particular iteration of the data. So in the case that someone has built a complex regression model, or whatever it has been, they don't want us to just suddenly be bringing in changes from a particular point in time. So in that instance, we would like to basically bring those changes in, but essentially reprocess our full history with those changes and provide that as a parallel stream, which clients can then upgrade to as and when they choose, keeping the old stuff simultaneously online. So yes, that's essentially where we are in terms of what we need to be able to do. I'm sure most of you know what AWS Lambda is. But in case you don't, it's a micro-compute service provided by AWS. It's serverless. Individual instances can be used to run a package or any code base up to, I think, a limited upper size. And that code can run for 15 minutes. So yeah, it's very flexible and it scales really nicely. And since no deployed infrastructure is required. So this is a brief, we try to keep our infrastructure as flexible and robust as possible. And this is a brief overview of how it works. So data is pushed up from the device. We consume that using Nginx, which just runs on Docker on a bit of EC2. And this is kind of the most crucial part. These two components form the most crucial part of our pipeline. From this point on, we can reprocess the Nginx logs as and when we choose, in whatever way we choose. But we need to be able to maintain a full entire history of those logs. So oftentimes the downstream pipeline might change, there might be cracks, things might go down, but as long as we have full continuous history of the logs, we can always go back and reprocess those from the source. So we then, at the moment, push those logs up in small buckets. So on a minutely basis, we push up 5 megabyte blocks of those logs to S3. And that S3 bucket has a trigger attached to it. When a file goes into that bucket, it triggers a Lambda. That Lambda is invoked, runs the code base, connects to, in our case, RDS, run it Postgres RDS for external lookups, and then spits the processed data out back into S3 for consumption by clients or to Google BigQuery. So this is a slightly simplified view of how it works, but essentially it gives you the gist. So what are the benefits of using Lambda? Well, it really nicely auto-scales. So essentially, the more files we put in the bucket, that just invokes more Lambda, and we don't have to worry about provisioning anything. We just basically write the code, push that up to Lambda, stick the files in the bucket, and those get processed. So essentially, from an architectural standpoint, it's incredibly simple. And then also, it scales linearly in terms of cost. So the more you use, the more you spend. We can just, if we want to reprocess data, we can just throw it all in the bucket and Lambdas will get invoked in order to process that data. Theoretically, we can do the thing I was talking about, having multiple pipelines running simultaneously. The reality is that that's more complex than it would first seem. You need to have multiple VPCs, multiple databases, and actually it's quite a lot of work to maintain that. So we do have blue-green deployment mode. So once one code base is live, we're deploying that all to, say, the blue branch, and then as we make changes, we make all of those changes onto the green branch until that becomes the live branch, and then we'll deploy green, and that becomes the new de facto live. But actually, it's not as simple, I think, as we would like it to be when we first started out. So what are some of the issues that we had with it and the motivation? So firstly, it's not massively fault tolerant. We have found that in our use case, so for lots of instances, I think it would be, but in our use case, we have dependence, say, on external databases, and you can get things happen like you have too many database connections open, for example. In that instance, you have kind of thundering herd style problems occur whereby your Lambda then, due to have some error in the data, will be then retried if it fails. And then, of course, if you already have a problem like overloading a database, the problem just gets worse and worse. So essentially, we found for us, it sits in a kind of locally stable equilibrium. It's fine while it's running. But if something throws it off, generally the problem doesn't self-write itself. It just gets worse and worse, and we end up having to kill the process, recover the broken period, delete that from database, reprocess that, etc. And that's a kind of manual process which we haven't successfully fully automated. As a result of that, we find that we generally over-provision the size of our database, which is not particularly cost-effective. So we would like to be able to handle way more connections and way more processing than we need, especially if we want to be able to rerun, reprocess historical data. Then we suddenly need much more capacity, requiring us to manually scale up and down the database. And finally, relating to one of the earlier points, there's an upper hard limit on how many of the Lambda you can invoke at one time. So I think that's currently 1,000 concurrent invocations. And although we are well below that limit, we would like to be ultimately. We know we're going to be above it eventually. So, and I know, having spoken to some of the AWS team, I think that's fairly non-negotiable. So most rate limits, I think, are negotiable. I'm pretty sure this one is not negotiable. So could be wrong about that. So what are our motivations for changing? Well, we would like to be able to have these multiple parallel pipelines running, but also resilience. I'd really like to be able to have a weekend where I have to be monitoring Slack to see if the infrastructure's gone down, and then spend my Sunday morning like deleting data out of the database and like reprocessing missing logs. That's, I'm sure anyone that's worked in a small rapid growth company can relate to that. And finally, the pace of reprocessing. So currently, we have, say, 3 years of historical data. It's tens of billions of records. If you take that 1,000 invocation Lambda count, it takes us about a month then to reprocess the data for any given new code base. That's a long time, and yeah, we would like to have that much more rapidly. So hence, I've been reading since really the beginning about large-scale parallel processing architectures, and I think, you know, of course, there's a lot out there. It had always seemed to be a pretty hard thing to tackle when, for a tiny team, there's only 3 of us, to perform such a large migration. But yeah, we started reading about Beam about 9 months ago, I think. Maybe a year ago. And Beam is an SDK which is maintained by Apache. It is essentially language agnostic and also runtime agnostic. So you can write your code in Java, Python, I think it supports other languages as well, and then you can run that on whatever MapReduce runtime you like. So it supports Spark, Flink, some other MapReduce runtimes, but for us, we use Google Dataflow. Why did it take us so long to start using it? Well, essentially, we have always been in the mode of finding out where our place in the ecosystem is. So we've had a lot of changes to the code base. We've needed to do a lot of things for clients, which have been quite immediate. And we've never really had that time window that has enabled us to really move to, do a big scale rewrite. So it is a big commitment because essentially it's a paradigm shift. It's not something where you can just, we did, of course, port large sections of the code base, but things need to be written not only slightly differently, but you need to be fundamentally thinking about your data in a different way when you move to large, parallel processing architectures. So there's conceptual understanding of how that stuff works, and then there's also the technical rewrite of the code. Also, when it was released, until recently, it only supported Python 2, which was kind of strange because our code base was in Python 3, so we had to actually down migrate. Fortunately, the last 2 versions which have been released are now Python 3. So yeah, we're back to Python 3, which is good. Yeah, cool. So this is essentially how does it work. This is a really, really top level description, but essentially you have a collection of data. that is essentially a stream. It can be either bounded, meaning that you're processing your collection of data in a batch, which is how we do it. So we run our pipeline on a daily basis, and therefore our data stream is bounded as a single batch. But you can run your pipeline continuously. So you could be consuming data continuously from whatever sources you wanted, and it can be constantly flowing through your pipeline. So it's it's kind of it's a different way of thinking. Essentially, then to this collection of data, you apply transforms. So Beam provides a large set of inbuilt transforms. They can be a bunch of different things. So they might be editing individual records. They might be reorganizing the way in which your records are contained inside the stream, and then the stream is then outputted again, and you continue this process as it goes down. So it's important to think of, it's kind of like, for me, I think of it kind of like a river or, a stream of data just constantly flowing through. Normally you write methods, and those methods then return arrays of data or in whatever way. This is more like seeing I don't know if anyone's used Keras, but it's kind of like similar to that in terms of how you glue these transforms together, and then the data essentially flows through those transforms. So a little bit about Google Dataflow and our decision to choose it. As I said, we're a really small team, so we're like 3 people in the tech department. So first off, it's fully managed. So we now, with the exception of what I showed you earlier, Nginx, we don't deploy any infrastructure at all. We only use managed services. Everything is serverless. So this is really, really awesome. Any individual job can run on up to 1,000 different compute instances, and each of those compute instances, even in the general purpose form, can have up to 96 vCPUs. So one job can run on about 100,000 cores of processing power, and you can run 125 of those simultaneously within your organization. So it's essentially like a lot of power. If we get to that place, I'd be really happy, essentially, if we max that out. But yeah, more power than we hopefully will need. So I'm just going to describe a couple of the Beam essentially provides you with a bunch of different out-of-the-box transforms for processing your data. I'm just going to describe a couple of them very, very briefly in order to give you a little bit of context for some of the issues that we encountered later. So first off is the Pardue, and this is kind of like a generic parallel beam transform. And you extend this class in order to process any individual record. So the canonical example often used in parallel processing is the MapReduce style architectures is the word count example. So in this class, for example, the default process method is then invoked with one single record from your collection, and then you can process that as and when you, however you choose, and then you yield the result continuously. So one of the things you need to get your head around here is that this is all you have access to. There is no overall application state, because all of these elements are being processed on individual nodes within your cluster. And those nodes, and especially in Dataflow, could be taken down at any time, and they could be spun up. So you don't have any global state to refer to. You don't have any idea of the future or the past. You only have what you can do inside this individual element. So often you want to organize your data before you pass it to the Pardue in order that you can process records together in a contextual way. Often you're going to need to do that, basically. Unless you're doing highly simplistic things, you're going to need to be able to do that. So one of the next a fundamental parallel data processing component is the GroupByKey. So using this component, you can then gather all records that correspond to one individual key together in one place. So this essentially, using these two transforms together, you can do quite a lot. Essentially, you group relevant elements in particular ways, and then you pass those to Pardue, and then you process those elements, essentially. So this provides you with lots of ways of organizing, reorganizing your data. With that in mind, I'm going to come on to some of the issues that we have encountered. So the first up is probably anyone who's worked in parallel processing is going to come across which called hotkeys. So here's a little schematic of your of your cluster, and when you're grouping the data by key, ideally, you will find your data will be grouped onto those individual nodes in the cluster, and ideally they're going to be shared out equally across the nodes in your cluster. But it's entirely possible that you have chosen a key when you group which has a disproportionately large number of records associated with it. So in this instance, what you will find is that that node that is associated with the key that has too many records is basically becomes the entire limiting factor for your overall pipeline. So you have all of this infrastructure up, potentially hundreds of nodes, and they're all waiting on one guy who is trying to process maybe half the data or something. So essentially, it's incredibly expensive and it's really, really slow. So we encountered I think we entered into the Beam project with super high hopes and loads of enthusiasm and made loads of progress really quickly. But we found that our rate of progress, basically, we would tank it through loads of development, and then we would get to these points where we'd be like, oh, maybe it's just not going to work. Maybe we just can't do our application in this way. I think it's almost always possible to overcome those points in the development, but yeah, you've got to keep the faith, essentially, because it can be very frustrating and hard to work out. And also, Beam doesn't yet have a really big developer community. So the Google support is of limited use. We are now connected to some of the Apache Beam developers, but nevertheless, finding out the information associated with some of these issues isn't actually super easy to do. So how do you solve this? Well, the most obvious answer is pick a different key. So often you will just happen to have chosen something which happens to be where your records are distributed unevenly across that, and you could easily choose a better key which will distribute your records evenly. Sometimes that's not possible. So for us, we need to do a lot of work associated with grouping data by location. So we need to know, geocode lots of places. We need to associate records with particular places in the real world. So we used some fairly basic kind of geohash creation in order to do this. Initially, we essentially build a hash from the truncated lat longs of any particular location and put everything into 1 kilometer blocks on the Earth. So everything lives in a 1 kilometer square. All of those records associated with that square will have a hash. This seemed brilliant. We were yeah, this is going to work, no problem. Seems really, really even. You imagine that's going to really be shared out well. Performed unbelievably badly. And then, of course, you realise, well, some places in the Earth are much more busy than other places. So, London or New York, a kilometre square in that place is obviously going to be super hot, and somewhere in the Gobi Desert is not going to be that hot. So, well, I'm trying to physically off, baby. Yeah. So essentially, in this scenario, then what we did is split split the data down into smaller chunks. So rather than using kilometer squares, where you will have some fairly small number of those, and some of those are then going to be mega hot on some of your nodes, we just split it into 100 meter squares. So you then end up with 100 times as many keys, which actually doesn't perform badly. Like Beam totally handles that larger number of keys really well. You're still, some of those are going to be hotter than others, but then you just have the chance to share out those hot ones, more evenly. So in our instance, most of our clusters come up with a couple of hundred nodes at most in order to process a day's worth of data, but easily then sharing out those hot keys across the entire cluster fairly evenly. So that was, so that's basically what ended up working for us. There was no possible way we could choose a different key for organizing the data in that instance. I'm sure there are other solutions, basically. Another thing we encountered, so there's showed you earlier, the basic form of Pardue. Often you want to be able to process other data along with the record that Pardue is given in its process method. So Beam provides us this really nice little auxiliary function, which is called a side input. So when the record is passed to the node to be processed, you can also pass it a lookup or an additional parameter. That parameter is going to be the same for every invocation of that process method, but you can then use that inside your code to do some additional work. So, for example, we often want to be able to use mapping tables. So we have ways of contextualizing the data, cleaning up device names, for example. Those mapping tables can be pretty big. And so, so coming back to my schema, that input then can be quite large. And if you think about what's actually going on here, every time that process method is being called, a record is being passed over the network. And often that record, the record is going to be very, very small. But if you're passing also then, many K or potentially megabytes of side input, like a really big mapping table, together with that record, you're dwarfing the basic distribution of the data with these super big files. So again, this was one of those points which we came to. We were okay, we needed to implement this code, which was already working fine on our previous infrastructure. When we got to this point, suddenly the whole thing ground to a halt again. And we're this was actually harder to debug because it's not immediately obvious on Dataflow to monitor your levels of network use, but that was kind of how we identified it. So suddenly we saw, when we're maxing out the network, and we identified that it's this issue that every time we're passing one single record, we're actually passing megs of mapping tables. So this was crucial to find a solution. And what we did was we found a couple of things, but essentially when the node is brought up by Dataflow, essentially if you were managing your own infrastructure, so if you had Spark, a Spark cluster, you probably wouldn't, well, it would be easier for you to fix this because you would just be able to load the data on all of your target machines, and then within your Pardue, you can then just load that data. So here we are we have a second method. So this start bundle method is also a default method of the Pardue, and this is run when the Pardue is initialized and a bundle of data is passed to it. So essentially this is run once per Pardue, and then the process method is called once for every single record. But you can do other stuff in here. So you can load data from your local machine. Using Dataflow, it's unfortunately, you can't customize your instance, and you can't customize the Docker containers that are brought up. So you can't basically provide your own Docker image. which was basically our first thoughts. We were like, okay, fine. Well, we'll just like bundle our data into the Docker image. We'll push that up to like, the Docker repository, and then we'll instantiate that image, and then we'll have our data there, and that will be fine. What we ended up doing was using setup.py. So when your package is installed onto the node, setup.py is run. And within setup.py, you can then open a bash script and use that bash script to then load data from permanent storage onto the target node. So essentially, we load data from a couple of different places. So load it from GCS, but then also load some data in from BigQuery, and then make that available on the local node. Essentially, then when you call your start bundle, merely load that data from the local file system into memory, and then you can, when your process gets called, you have a nice in-memory dictionary or array or whatever it is you want. We also do some other stuff in here where we spin up Redis on the local machine. So for lots of instances where we are looking at smaller records, which we need to look up more rapidly, then Redis is also really awesome. So yeah, there's a few of those different little tricks that work pretty well. And yeah, that was kind of a mission to work that out. Anyway, then next thing is database transactions. So we have this stream of data which is being processed continuously. So each day's worth of data is being processed. That's not the only thing that's changing. That data is also altering stuff which we have in permanent storage. When we're in our Lambda architecture, that's fine. We can write easily back to RDS from inside Lambda, but you can't basically create a database connection within a Pardot. That's just not practical from either a timing standpoint or a network latency standpoint. So to solve this, basically, but you can have as many P collections of your data. So you don't have to only be processing one stream of data in your pipeline. You can have as many streams as you like running through your pipeline. So essentially what we do is then take our persisted database, load that into a P collection, and then run that simultaneously through the pipeline, making changes as we need to, and then essentially at the end, when the pipeline terminates, we just write that data back to either BigQuery or GCS as we need. So that's kind of works well for us. I'm not sure if it would work if you were running essentially like continuous pipeline. It works for us because we're running it in batches, and so you have these sort of very obvious points where you want to like write your records back. I think you might have to think about that a bit more carefully if you are running stuff in a continuous stream. So yeah, like what's the payoff for us look like? Well, it's super stable in general, and we can run as many versions as we like. So essentially our workflow now looks like write a bunch of code when we get to release point, push that code up to GitHub. GitHub runs the tests on Circle CI. If those all pass, then we essentially use another service, a Google service called Cloud Composer. This creates a Cloud Composer template, pushes that up to Cloud Composer together with all of the Beam pipeline code. So if you haven't used Cloud Composer, again, it's another serverless service. It's essentially their version of, Google have a lot of versions of open source stuff, but it's their version of like a product called Airflow, which was originally, I think, built by Airbnb. But essentially, it's like super cron on steroids. It's like really awesome. You can schedule loads of stuff. You can configure it in tons of different ways. It's really nice UI. It's really good for us because we can then like reprocess data as and when we want. Yeah, so anyway, I strongly recommend checking it out if you haven't. Cloud Composer tasks kicks off then on the daily schedule, the Google Dataflow job, and that job then writes the results into BigQuery, from where we then export it in a variety of different forms to clients as I said before, when we push another version of code, that essentially then can just automatically, we just bump the version number, that will just like bump a version, create a new template, push that up, and all of these will then run simultaneously in parallel on a daily basis. And works pretty well essentially, and that's about it really. So happy to answer any questions. I am by no means an expert on any of this stuff, parallel processing architectures in general, but I'm happy to answer anything I can.
Any questions?
Did you have any problems with that?
Yes, so yes, we've had quite, particularly because so we were running like loads and loads of very small tasks, and essentially it's not really designed to do that. So we were running like tens of thousands of small jobs, but it's not really oriented for that. So we export the data 1 record per day per country. So for each of our feeds, that's 250 files per day. You look at our entire history, 1,000 days, a bit more. You start processing all of that simultaneously. Essentially the scheduler gets snarled up because it's essentially designed to run more like fewer long-running tasks. There's a lot of overhead in the creation of a task, and rather than the execution. So we built basically a bunch of custom custom tasks basically, which then aggregate those jobs into larger blocks, so you can then just like run one job, and that job is essentially doing lots and lots of individual writes or whatever it is. So because if you go in and you look at just how much time it takes just to spin up the job, it's like ages, like multiple seconds. So but overall the experience has been good. It's really nice way of the UI of Airflow is really good. It gives us really good feedback about which jobs have completed successfully. It's generally really nice. It's moved on our export of data, particularly has made that process like far more straightforward essentially.
How's the bill comparing to before?
Okay, so variable. Generally much lower. So now I can't work out actually. I've been working on something else, and then our build has broken. But like suddenly, it was $20 a day for processing about 200 million records. Compared to, so I could tell you, I could work out that's a lot cheaper. Basically, is all I can say. When overall, one of the main, I didn't put price in, but price is like a massive factor. One of the better things about it, which I also didn't put in here, is that it scales better than linearly. So when you're doing like large groups, but group by keys or co-group by keys, if we say, okay, our data falls into however many keys that is globally for a bunch of geocoding, that's kind of like the hard work, essentially, is like creating each of those keys. Allocating more data to each of those keys is like less work, if that makes sense. So once you've done the kind of hard bit at the beginning, adding more data doesn't necessarily doubling your amount of data is not going to double your amount of vCPU time. So what this opens up for us is, rather than reprocessing single days at a time, we can reprocess like months or entire years all in one go in one pipeline. But yes, overall the price is a lot better. But you just can easily get these things where, like, if something breaks in the pipeline, all of the nodes then stay up, and suddenly our bill the other day went from $20 to like $200. Like I was like, what's going on? Like suddenly it's, and then $200 a day is a bit less of a joke if you're a small company who doesn't have. And my CEO was giving me a hard time about that. So yes, generally though, really good. You don't have to, as we said, you then don't have all these ancillary services. You don't need additional databases. Everything is in one kind of like pipeline. So not only from that perspective, but from the perspective of the clarity of the code base, rather than being fragmented, shared across multiple lambdas, some is here, some is there. Everything is in one place. Like new developers can come in, they can look at the code base, and it's just like, you know, I can show you. I don't think I have it actually. Yes. Also, Dataflow provides you really nice UI, so you can see the entire pipeline laid out in that way. So yeah, it's good.
How do you actually collect the data? So you said.
Okay, so we have basically we have partners. Those guys are mostly small app publishers. So they generally have either hundreds of thousands or millions of users. And then we have an SDK, which basically they install, and that SDK runs kind of fairly continuously. So yeah, anyone's interested in GDPR, that's been quite an interesting perspective. We made a jump fairly early in GDPR to be completely anonymous. So we don't have no information. I mean, yeah, there's issues always around location data and how that can be used in regards to individuals, which is potentially something we've had to navigate. So yeah, we do a bunch of stuff in order to safeguard the privacy of our users. But yeah, their data comes directly from mobile.
Thank you, Eisenberg. I don't have any more time for questions. And we have Marco, who's going to talk to us about extracting text from data, or the other way, data from documents, and then doing something crazy with them. Cool. Topics from documents. Awesome.
Okay. Yeah. Thanks for joining me, and thanks for having me one more time. So, a presentation on topic modeling, so extracting topics from large collections of text, and I have a bit of a demo as well, which is going to be on GitHub. Well, it's already on GitHub, and the slides are going to be published in the meetup page. And started out as a joke, but if you like patterns like me, well, maybe you notice there is a bit of a story here. So every September, we come back here at the London Python meetup to talk about natural language processing. You're not tired of me, apparently, yet. Maybe you can suggest a topic for next year. And if you notice, typically I tend to give presentations that are introductions, so I don't. I'm not here to impress the experts. So I'm here to get more people interested in doing stuff with language. And the topic for today is topic modeling. About myself, just quickly, I work as an independent consultant in the data science space, so specializing in natural language processing, but also machine learning, anything interesting with data. I'll do it, and I do a lot of training as well in the Python and data space. Apart from work, in the evenings and weekends, I help co-organizing the Python London meetup, so one of the other user groups in London working on Python, and I'm chairing the annual conference that we're having, that we run as a community event, that we use to raise money for non-focus. So coming at PyData London, essentially, you contribute back to the PyData ecosystem. And you're the first one to hear about this, but we have provisional dates for the conference of next year. So that's news from earlier this week. It's not official yet, but very likely to happen in May next year. So keep an eye on that as well. Now on to the topic of the presentation. So topic modeling. I'm also happy to continue the conversation later on the broader applications of natural language processing, depending on the interest of people. And the assumption is that maybe some of you have some basic knowledge of NLP, or they tried something with NLP, but really this is an introduction for beginners. So why are we talking about topic modeling? The idea is that you might have a big data set of text and you don't know much about it. You just want to know what's going on in terms of a topic, what people are talking about in this data set, which was also the original topic of the presentation. What are they talking about? And the idea is that when you have a lot of text, potentially even millions of documents, you don't want to read them all. You want to automatically have an idea of what is going on. So that's what topic modeling is about. Topic modeling gives you a bit of a bird's eye view on the whole data set that we call corpus in linguistics. And if you're looking for a connection with machine learning modeling, we are in the unsupervised corner of machine learning. So essentially, there is no notion of making a prediction for a correct type of output. We're not trying to predict a category or anything like that. We're simply grouping things together to see how topics are distributed. In terms of pros and cons, because we are in the unsupervised domain, there's no need to have labeled data. So whatever kind of text we have, we just throw it into a topic modeling algorithm, and we're going to have some output. On the negative side, we don't have any notion of expected output. So how do we evaluate what we see? So assessing the quality of our topic model is a bit of a challenge in itself. So often we use topic modeling for exploratory analysis to just know a bit more about our data. So that's the idea for this discussion. In terms of input and output, then the idea is that you throw a collection of documents, any number of documents, and you don't really know how many topics to expect. But typically, topic modeling approaches will ask for a specific number of topics. So you need to provide the number of topics, k or n, as an input. So finding the ideal number of topics is also another challenge in itself. And given this big collection of documents, then what is going to happen is that the topic modeling approach will give you the topics, the number of topics that you're asking, as well as the word distribution. So you throw a bunch of documents in input, and you will see topics like, it looks like movies or sports or finance, market, investment, whatever. And you see how words can aggregate together. So that's the idea, that's the overall idea of topic modeling. Apart from the overall topic distribution across the collection, you also have a notion of topic distribution within documents. So the idea is that each document will have a distribution of topics, and each topic will have a distribution of words. Behind some of this idea, there's nothing new. We go back to the 50s to understand where we're coming from. And one of the foundational concepts from linguistics is the distributional hypothesis. And when talking about the distributional hypothesis, typically people make reference to John Firth, a British professor of linguistics, who in 1957 described the distributional hypothesis, saying you shall know a word by the company it keeps. Just like you shall know a person by the company they keep. If I want to know about you, I look at your friends and I guess about your personality. The same idea you can apply it to words. Another professor of linguistics gave a similar description of the distributional hypothesis. Words that occur in similar contexts tend to have similar meaning. So basically, we're looking for word co-occurrences. We look at words that occur together, and we use the context where we observe different words to understand and approximate the meaning. And the notions that have been developed from the distributional hypothesis then have been applied in a bunch of different natural language processing techniques. So looking at words that occur together, one of the key data structure that we are going to build when we analyze large collections of text is simply a term document metric. So we build a big table where for each document we keep a track of how many words and what kind of words and how often we see different words. It could be simply a raw count, or it could be some kind of normalized frequency distribution. Anyway, we know basically which words occur with which other words. Now moving on towards building topic models from here. One of the main approaches for topic modeling still nowadays is latent direct allocation, or LDA in short. It's been around for a while. It seems to be still widely used. And the key idea, as mentioned, each document will have a distribution of topics, and each topic will have a distribution of words. Looking at the name, latent direct allocation, latent as in hidden, what we can observe are only the words. We see the words in documents, and we don't really know what's going on behind the model. So how the topics are distributed and how the internal parameters of the model work together basically are hidden variables. And the other part of the name, direct allocation, there is an assumption here. We simply have a particular type of probability distribution for the topic. So we assume that topics are distributed with this particular probability. So with a direct prior, that's what's going on behind the funny name. So LDA is still nowadays the main approach for topic. In terms of how well a topic modeling algorithm is doing, as mentioned, we are in the unsupervised learning corner, so there is no notion of correct answer really. So people typically try to put the topic modeling task in context. So if you have some other task and topic modeling would be part of a pipeline of some other machine learning tasks, then you can evaluate the output of your topic modeling using some extrinsic metric borrowed from other tasks. Or if you insist, you can look at the internals of the model and come up with metrics like topic coherence that I'm going to tell you in a moment, or something similar. Essentially, you come up with a score that will tell you how well your model is extracting topics. But for me, the most useful part is asking the question, what can I learn from what I see? So using the topic models to learn more about your data, the aspect of knowledge discovery is much more interesting when running topic models. So I often use topic modeling in exploratory analysis. I have a new data set. I don't know much about it. I just run topic modeling and I try to make sense of the output. So learning about the data is really how I tend to apply these unsupervised techniques. And because we are talking about high-dimensional models anyway, they are kind of difficult to picture. So there are a lot of tools that provide visualization, can be useful to navigate large data sets. So using data visualization tools will give you some additional insights rather than just digging into the individual probabilities. I mentioned topic coherence. It's one of the main metrics that we can use to assess topic quality. If you like maths, there are some interesting relationships with information theory, and in particular PMI, pointwise mutual information. And you can also use it to have an idea what the best number of topics is.
No, it's all right.
Right.
Just a microphone.
Yeah, it's all right. So topic coherence is just a tool that you can use as a score. Sometimes people try to get the best topic coherence. I think it's just yet another tool that you can use to understand more about your data. Yeah, so I gave you basically a bunch of ideas on concepts related to topic modeling. Now I just want to give you a brief demo which is in the form of a Jupyter notebook. It's on the GitHub that I linked earlier. This would be a bit of a long session, probably kind of 1 hour that I run as a workshop. So I'm going to skip on a couple of details, in particular the first part on the configuration. There are some warnings that are popping up depending on the combination of version numbers for NumPy. That's one of the libraries trying to do something funny with the generators. I'm using a data set which is a data set of news groups. So emails, essentially kind of messages categorized per topics. And I'm going to cheat a little bit. The point of topic modeling is to extract topics when we don't know what the topics are. I'm using some topics that I know about, and I just try to see if the model will give me back something related to the original label. So I cherry pick 6 topics from the dataset: hardware, like autos, space, something about sales, something about politics, and guns, and religion. About 3,000 documents all in all. So that's a kind of piece of text in the space topic. So Apollo, astronauts, trained, meteor, blah, blah, blah. So words that are reminding you about space. The starting point of every end-to-end NLP pipeline is some decision about basic pre-processing that we want to use. In this example, I'm just doing a basic tokenization where given a chunk of text, I break it down into individual tokens, words, and punctuation. And that's a bit, it's far from being enough, and we already know this. It's just a first step of the iteration. From there, I would use the library GenSim, which provides a bunch of topic modeling algorithm. It comes with also a set of facilities to convert the text into our term matrix representation that we mentioned earlier. And we go from a chunk of text into a numerical representation. So each word will be mapped into a particular component. We keep track of the frequency. That's how a single document looks like in the term document matrix, so frequencies and word IDs. From there, this is essentially a view on the actual words that are mapped together with their frequencies. It's all good, and then we can dump this data structure into the LDA algorithm. Now, for a data set of a few thousand documents, I expect something within 1 minute for training. So you throw your documents in. Here I was waiting for 45 seconds, and then the model is trained. Once we train the model, we can print out the topics without knowing. Pretending I don't know the topics. I was starting with a number of topics equal to 10. It's a fair kind of starting point without knowing anything better. And the topics that are coming back, because we did a horrible pre-processing, are actually horrible. So we have punctuation, we have the, of, with, to, and so it's a lot of stuff that is not really useful. In the first iteration, the idea is, as we say in machine learning, garbage in, garbage out. If you do some better pre-processing, then the model will tell you something better. So, can we do better? Yes, definitely. We should, first of all, remove the punctuation, remove what we call stop words, all the words like the, of, with. Some libraries come with a list of predefined stop words, then you always need to enrich it with your extra keywords. So things like the contractions are not usually captured, apostrophe S, apostrophe double L are not really captured by these libraries. And then there could be something that is still missing. So I typically enrich my list of stop words, and I go to the pipeline again, doing a bit more of the same with the term document matrix, throwing the data structure into the same LDA model, and now well, the first topic, space, data, launch, NASA, it looks a bit more meaningful. So maybe there is a topic about space. The second one says gun, firearms, build, control. So something about guns and politics. So things are starting to emerge now. That's fine. There are still a lot of bits and pieces that are not very useful. If you see topic number 3, Q, H, U, that's a bunch of rubbish essentially that went through the pre-processing pipeline. So one thing that I could do is remove the extremes of the distribution, something that is too frequent, probably not very helpful, and something that is too rare, also not very helpful. Typically, text will be distributed in a very long tail distribution, following what is called a zip flow. And the idea is that the interesting stuff is in the middle. So get rid of the very frequent and the very rare words is something sensible. And I'm reducing basically my term document matrix. More of the same, rerun the model, and that's what typically you would do, right? Iterate a few times until you find the ideal pre-processing pipeline. That's where you spend most of your time cleaning data and preparing the data. So now I have something about cars and engines. So it's looking okay. Sales, new offer, shipping. Probably another topic emerging there. And then, yes, I could dig into the individual keywords and try to read all the topics. It's a bit of a tedious exercise. So what I like to do at this point is some data visualization. And in particular, for LDA visualization, there's a library called PyLDAVis, which is smart enough to recognize the main natural language processing libraries dealing with LDA. So it has a nice interface with GenSim that we used earlier. But also, if you use scikit-learn for machine learning, it has an interface for that as well, and probably a couple more things. If you run this one, you can go get a cup of tea, come back in a couple of minutes, and some nice visualization will pop up. On the left, you have a bit of a map where the topics are represented in 2D. The size of each circle is basically the size of the topic itself. And looking at the relative distance between topics, you can see which topic is more similar to which other topic. So the idea is that topic 1 and 4, whatever they are more similar to each other compared to 1 and 7. Okay. So in the projection, looking at a 2D screen, you miss out on some meaning. The only thing that you capture is a relative similarity. So the dimensions don't mean anything in particular. Similar things here in low dimensional space are also similar in high dimensional space. That's the idea. So with this tool, I can sort of go around and click on the topics. Notice how the topics are labeled with number. We don't have a topic name. Okay, that's not coming from the modeling. That's our task, finding out what the topic is about. So I click on the topic, and I look at the topic distribution here. So Mac, Apple, Drive, card, software, disk. So it looks like this is about hardware. In the visualization, I also have a slider that is changing a particular value for London. And the description of what is going on here is at the bottom of the picture. Basically, I want to see a list of keywords sorted by internal relevance, and you can play with this parameter to change the topic distribution. So if I'm sliding to the max, I see the words that are rearranging, and you see how the bars here are not very red anymore, they're more blue. So red means highly relevant within that particular topic, and blue means highly relevant across the collection. So sliding towards 1, I have general purpose keywords, and sliding towards 0, I have more specialized keywords. So here you will pick up a lot of jargon. Okay, so that's highly specialized terminology. And on the opposite side, you will pick up general purpose words, so maybe less relevant for the topic, but more understandable for the average human being. And probably sliding somewhere in the middle, you will find a bit of a sweet spot. Then you can go across all the topics and see that we have something about God and Jesus. So there was the probably the religious topic. Next to it, we have nothing in particular. So there is always a big topic coming up, which is capturing the general purpose words. So from the previous configuration, 6 topics we had. I would expect at least 7 or 8 topics to emerge naturally from those, because apart from the specifics, guns, cars, Mac hardware and whatnot, we also have a general purpose topic, a kind of a catch-all topic for the other words that are coming up frequently, not too frequently to be removed, but at the same time they cover a bit of everything. So I will spend at this point, anything from a few minutes to a couple of hours to investigate the individual topics, rearrange the word distribution, and see what I'm dealing with. But I also want to go a bit further and do some of the topic scoring that I mentioned earlier. So GenSim comes also with a notion of coherence score that you can use to capture whether a model is doing well or not so well. Here I have just a couple of examples of scores, how you can train a good and a bad model, and the good model will have a better score, hopefully. So higher means better. The number in isolation doesn't tell you much. You use the numbers as a comparison tool, so you see which one is higher. But the absolute number per se, not very useful. And finally, you can use this idea of coherence to find out what is the best number of topics from a given data set. So we knew about 6 topics coming up from the data. I told you there is typically one extra topic, which is the general purpose keywords. And now I'm running what people would call tuning, or you can call it brute forcing if you prefer. That's a for loop that goes across a number of values, trying to find the coherence score. So this is literally running the same model over a range of numbers, and then we can either plot the results of the coherent or just investigate the numbers directly. And here I see that as I increase the number of topics, we go up and down, and in particular, it looks like the best coherence is coming with 8 topics. So given what I see here, I would rerun the model once again, specifying the value for the number of topics as 8, and then I would try to dig into the words a bit more, as I've done. And that's kind of an end-to-end exercise of exploratory analysis. Now, that's kind of wrapping up. The idea of doing topic modeling is to have a bird's eye view on the data set as a whole. So it doesn't give you specifics on the internal structure. It doesn't tell you, what the topics are about. It doesn't tell you any label for the topic that you find. It doesn't tell you how many topics you should have. This is all up to you to find out. We're still talking about unsupervised learning. That's important to remember. And all in all, it's just a great way to do exploratory analysis, to know more about your data, to kind of find out things you didn't know about your data. And it's a fun tool to play with, very useful when dealing with the large collections of text that you just need to understand better. So yeah, that's the overview on topic modeling. The summary with Python is that we have a lot of tools available. I mentioned GenSim. There's another library called NLTK that was in the picture, nice for learning about NLP. There is another library that I didn't use here called Spacey, which is a bit more production ready. We've seen the PyLDA Viz for data visualization. So a lot of tools to play with, and I simply hope that people get curious and give it a try on your data or some public domain data. So that's all for me. Happy to chat more about NLP in general now or maybe later at the class. All right, thank you very much.
I got a question. Does the tools that you use, do they handle text? How do you just throw random strings at it, or can you give it like files or like PDFs? Even?
Okay. No, the pre-processing is up to you. So GenSim is expecting a collection, an input, which is a sequence of documents, where each document has to be a sequence of words. So you do the tokenization, the parsing, whatever. So I was developing a little pre-process function that does the breakdown, removing keywords and so on, and that passes the text as a list of strings. You can pass it as a generator if you have a larger collection. So as long as you can look through it, So a sequence of documents, and each document a sequence of words, or tokens rather. That's what the GenSim library is expecting. Other libraries could have a different interface. But the usual story is that the pre-processing is up to you. Yeah.
Any other questions? No? Okay.
Have you tried like comparing these algorithms, to other ways like Word2Vec or something? Do you know what I mean? To see if it comes up with similar kinds of topics. Do you do that sort of like cross?
Yeah. So yes and no. We're talking about two different tasks here. So Word2Vec gives you a representation per word. Okay.
Yeah.
So you know which words are similar to each other, and then you can do the nice compositions. So you combine different words to end up with new concepts. So you get different output. Right. You can still, so apart from Word2Vec, there's also Doc2Vec, which does the aggregation per document. So you end up with vectors representing documents. Or you could use Word2Vec aggregating per class. So you pretend that each class is a kind of a single big document, and then you can come up with a class similarity. But they give you different views. So I would use all of them, yes, but I wouldn't be too stressed out about comparing things, because we're talking about different output here. So they tell you a different story. But I would try to see if what I see in the topic modeling, as in there's a topic about space and moon and whatnot. I try to see if those words are actually similar across the whole collection. Yeah.
Cool. Thank you for coming. If you want to go to the pub, maybe follow Marco.
That's where it is.
Thank you.
It's very good. You get to very interesting, very broad.